So last time we introduced Kadanoff's idea to form a block spin, formalism of the Ising Hamiltonian, and there are two important assumptions that we introduced last time. The first assumption of Kadanoff is that the effective Hamiltonian before and after we made this block transformations are effectively having the same form, okay? Meaning, apart from this renormalization of the coupling constant, which we will discuss later, so these two Hamiltonians have exactly the same form. And therefore, the free energy density between the unscaled and rescaled form have this relation. So they differ by a factor of b to the power of minus d, where this b is a scale factor, which we would like to expand lattice constant to the size of the block spin. So remember that this is what we say, that the original lattice is actually reorganized in such a way that the spins inside this shaded area form the block spin with the size b times a, where b is the integer multiple of this lattice constant, little a here. So upon this rescaling or the block spin transformation, the Hamiltonian looks exactly the same. So we will discuss that assumption in just a moment, but let me just finish the assumption number two. Assumption number two is that this rescaled coupling constant, little tb, and rescaled this magnetic field, hb, takes this power law form as a function of this rescaling factor b in such a way that this tb is given by little t times b to the power of yt, and likewise this hb takes this form of h times this b to the power of yh, whereas both yt and yh are unknown exponents to be determined later. So these yt and yh is a function of a critical exponent that to be determined from our RG, renormalization group analysis, but not at the level of the Kadanoff's block spin. So combining these two assumptions, we are able to derive the Witten's scaling hypothesis that we will discuss in just a moment. So let's just discuss this first assumption. So you may wonder why that the Hamiltonian after the block spin transformation has the same form as the unrescaled original Hamiltonian. Of course, this is assumption, okay? But this assumption is some sort of approximation. Okay, of course, you can imagine that there can be not just nearest neighbor block spin interactions. Suppose that the original Hamiltonian has the second neighbor interaction. For example, we have not only just nearest neighbor spin interaction, but the second neighbor interactions. Or we don't have nearest neighbor, but just a second neighbor interaction. And we form the block transformation as suggested by Kadanoff, and then we get this effective Hamiltonian as a function of the block spin. But of course, there will be many couplings involved here as a coupling between or among these block spins. So there may be additional couplings between these block spins in addition to the original couplings suggested in the original Hamiltonian. So what I'm trying to say is that this assumption could be regarded as approximation. So approximately, we could consider the effective Hamiltonian before and after this scale transformations approximately the same. Of course, they differ by some details or subleading corrections, but so we will actually confirm this assumption based on the Wilson's idea of a renormalization group analysis precisely at this point. So, of course, there will be additional coupling constants generated upon this rescaling processes. We can say that up to leading order in RG, so we could neglect all the other different couplings that are generated upon this transformation, and we only keep the coupling are the same form as the original one. So you could consider this assumption as approximation. So that's the remark. And this approximation is actually getting more and more rigorous as we progressively perform such scale transformations many times until we reach so-called fixed point value where the coupling constant do not flow. So that's the justification of this assumption number one, that the effective Hamiltonian takes the same form as the original one after the scale transformation. So that's a very important comment and remark that we need to remember. So therefore, this have the same form is actually only at the level of approximation or assumption. So we assume that they have the same form. But the other additional terms that we'll throw away are irrelevant upon RG transformation, and that will be justified later after we perform this RG analysis. Okay, so at this point, this is just assumption and a sort of a approximation. Of course, the Hamiltonian before and after the scale transformations may slightly differ from one another, but this is the Kadanoff's very important assumption, which will be justified later. Okay, so let's just combine these two assumptions, and immediately, if we plug in this power law form of this TB and HB back to this conclusions based on the assumption one, then we immediately get this kind of a transformation or the relation between the free energy density before and after the Kadanoff's rescaling processes. So here, the Fs as function for little t and little h is the original free energy density, and on the right-hand side, this Fs as a function of this Tb and Hb is the rescale free energy density, so they differ by a factor of b to the power of minus d, as we derived previously, and there's a relation between Tb and T and Hb and H, and the relation between these two sets of coupling constants are this form, that they differ by a factor of b to some power of yt or yh. And from here, we could actually manipulate this scaling factor little b here, since b is actually arbitrary. So as long as b is larger than 1, that's fine. So we can choose whatever value of b we like to actually modify slightly the form of this relation between the free energy density before and after this scale transformation. And we could particularly choose b to be this magnitude of the little t to some power of minus 1 over yt, so that we can cancel the first degree of freedom is a little t. So this little t times b to the power of yt becomes just a plus minus 1. And then we could instead just plug in this b to the second variable here, this little h times b to the power of yh, and so this factor becomes h times t to the power of minus yh over yt. So in other words, we kind of removing one degrees of freedom, then we could just kind of use this specially designed this scale factor b to actually look at the free energy as a function of this combination of this h and t to some power. And this, as you can see, that this form looks very much similar to the Witten's hypothesis for scaling, because now you could simply just say redefine these parameters that we just introduced. For example, if we redefine this yh over yt as delta, and that delta is the same as the Witten's hypothesis, and we will show that this delta precisely corresponds to Witten's hypothesis. And also, d over yt, suppose we define this as 2 minus alpha as Witten's hypothesis, then we could rewrite this free energy density in that form, which is precisely in Witten's scaling hypothesis. So in some sense, Witten's scaling hypothesis is not coming out of nowhere, because it's already hidden in this relation of Kadanoff's block spin transformation. It is the first step of a RG transformation that we will introduce later. So now let's just derive this delta and 2 minus alpha based on this Kadanoff's scaling relation formula that is consistent with Witten's scaling hypothesis. So for example, if we simply use that little SFS free energy density here, then we could simply just get the specific heat by taking the second temperature derivative, a little t derivative of this capital F function respect to the little t, and immediately you get that d over yt is precisely 2 minus alpha. And then we could likewise prove that this delta by comparing this Wheaton's scaling hypothesis and Kadanoff's scaling relations, that they should be identical. And therefore, this capital delta is nothing but the combination of this YH and YT. And this YH and YT are both functions of this critical exponents, alpha, beta, gamma, and so on. And next step is that we could check this correlation length or the critical exponents corresponding to the divergence of the critical correlation length exponent. So this C0 represents the correlation length of the original Hamiltonian, which diverges as little t to the power of minus nu. But as we discussed last time, that after rescaling, after this block spin transformations, this correlation length got reduced by a factor of little b. But still, we get C0 is proportional to t to the minus nu, and we know that b is chosen to have that form, t to the power minus 1 over yt. So if you plug that in and compare this kind of a two power law dependence and compare the exponents of this power law in t, then we can immediately see that this nu is nothing but 1 over yt. As I mentioned, YH and YT are all critical exponents, a function of critical exponents. So then you could simply just get rid of the YT by replacing it by this 1 over nu, and you immediately get the scaling relations that we just derived previously, that 2 minus alpha is the same as d times nu. So similarly, you could derive other scaling relations based on the Kadanoff's scaling, not hypothesis, but scaling form of a free energy density, and which is consistent with Wheaton's scaling hypothesis. For example, you could check this kind of identity that we introduced earlier. The alpha plus 2 beta plus gamma is exactly 2. So you could start from the Fs, the free energy density over there, the scaling form of the Fs, and then you could take the derivative of this Fs with respect to, say, temperature and the field, and so on. Second derivative is temperature and the field, and derive the critical exponents alpha, beta, and gamma, and then you could check that they satisfy this relation. It's very important to know that this is not a coincidence, because the underlying physics is all about the power law dependence of these physical parameters, observables, and this power law dependence is hidden in the power law divergence of the correlation length. Of course, there will be a microscopic length scale involving here, but as a general rule, this correlation length divergence in the power law fashion will lead to all these non-trivial critical exponents that we see here. And the relation between those scaling forms and in free energy density and also in critical exponents is actually hidden in the Wheaton's hypothesis, but the Wheaton's hypothesis is actually deeply rooted in Kadanoff's block spin procedure, that we could transform our Hamiltonian in terms of the block spin language, and we assume that this block spin works the same way as the original degrees of freedom, and then they follow this power law relations upon this rescaling. So then we almost complete the circle, except at the level of Kadanoff, we don't know what this YT and YH, the value of them, and we will figure that out later when we perform this RG. So let's take a short break. When we come back, we will use this scaling form for the free energy density and to get this non-trivial anomalous exponent of a two-point correlation function that we advertised some time ago. So let's take a short break. So let's continue asking this question. So based on Kadanoff's idea of a block spin, can we get this non-trivial anomalous exponent for this two-point correlation function, which is defined here for the spin-spin correlation? And we can take this scaling ansatz of free energy as a starting point. Then we could use the idea of a Kadanoff block spin by rescaling this lattice by a factor of b, and then we could relate this the Green's function of the block spin system to the original correlation functions, and we could get the information of this anomalous exponent eta. Especially we mentioned that for a two-dimensional Ising system, eta takes the value of a quarter. For a three-dimensional system, eta is very small. But in the Gaussian theory, Landau's mean field theory, eta is identical to 0. But we know that this is not the accurate result, so we need to improve that. But how can we do that? Well, Kadanoff's block spin idea is one way of getting this non-trivial anomalous exponent eta. So let's just start from calculating and relating this GB, this block transformed Green's function or correlation function defined in the language of the block spin variables as capital I and as capital J. And let's just follow the definition that we already discussed for this as capital I, which is simply just the average over entire spin degrees of freedom over a block and divided by this average magnetization m bar b of that block. And m bar b is nothing but this by definition. So look at this kind of a Zeeman term, the magnetic field coupled to the magnetization, and to actually get the idea of the transformation for this m bar b, because we will use that later. So we know that this factor Zeeman energy integrated over the spatial degrees of freedom is actually a dimensionless quantity. It carries no dimensions. Therefore, after we do this block transformations, this integral of the Zeeman energy still remains dimensionless. So we can use that property to perform this scale transformation, the block spin transformation, and we could introduce this ym, this exponent, in a similar way that we introduce this yh for this field, and then we could just plug in this kind of a power law scaling form of these parameters r, h, and m back to this Zeeman energy, and we get this overall factor of b to some power minus d plus yh plus ym, and times this block spin degrees of freedom of the Zeeman energy. So, but we know that this should be a dimensionless quantity, so which means that this exponent for this in this vector b to some power, that power should be 0 because it does not depend on the scale anymore because this is dimensionless. And therefore, we immediately get this relation that this yh plus ym is equal to the dimension little d. And therefore, we could just rewrite this m bar b as a function of m is given by this m bar times b to some power, and the exponent is ym, but ym now is actually d minus 1h. So likewise, we could just try to get the relation between h and b by considering this again, the Zeeman term, but now we focus on this kind of a block summation. So the original Zeeman term, after summing over all this individual spin degrees of freedom, is given by the same summation, but in this block variables. Okay, but this is the same as this hb times this block spin degrees of freedom, and therefore we immediately get this hb as a function of mb bar, which is h times mb bar times b to the power of d, and we immediately plug that information back to this relation between m bar b m bar, and we get this relation here. So m bar b is given by m bar times b to the power of yh minus d, so this will be used in just a moment. Okay, so now let's repeat the definition of this block spin variable one more time, but this time we try to do power counting as a function of a b to some power, and we count the power exponents in b when we write down this block spin degrees of freedom. So then we could plug in the definition of a GB in a block spin form, and we could simply just plug in this factor of b here to actually count how many powers in b are there when we write down this GB. And then we could just simply just plug in the relation there, okay, that we just obtained, that m bar b is actually m bar times b to the power of yh minus d, and which is precisely this. And then we could just cancel all this factor of b to some power and get clean notations in this factor b to some power, and then finally we arrive this identity here. So GB in terms of the block spin variable as function of RB and TB and HB is given by the b to some power, and the power exponent is 2 times d minus yh times the original unrescaled Green's function. So this is the relation between the scaled and unscaled Green's function for a spin-spin correlation function. And then we could start from here and we can calculate this anomalous exponent eta that we wanted to derive over there. So let's take a short break. When we come back, we'll finish this derivation based on Kadanoff's block spin. Before the break, we just derived the relation for this 2-point correlation function, before and after the block spin transformation. And the relation is given by this. So they differ by a factor of b to some power, and this power exponent is given by 2 times d minus yh. So this is the scaling form of a correlation function in the context of the Kadanoff's block spin. So this is the block spin transformation where this RB is reduced by a factor of b because our unit is enlarged, and the TB is scaled by b to some power of yt and hb by yh. So as I mentioned just a moment ago, that this scale factor b is arbitrary, and so we could choose whatever convenient for us. So first, let's just set this b, the factor b, to be t to some power 1 minus yt, minus 1 over yt. So we could just plug this assumption, our set for this b factor back into the relation, the scaling relation, or the scaling of a correlation function. And we get this a little bit messy power law in t. So when we do so, we actually get rid of 1 degree of freedom, namely the t is actually gone because TB is actually t to some times b to the power of yt, and if b is defined by t to the power of minus 1 over yt, and you plug that in, you get precisely the cancellations of TB. So TB now becomes 1 because this is trivial. Now TB under the definition of this b is actually t times t to the power of 1 over yt and to the power of yt. So this is given by t times 1 over t, which is 1. Okay, so the reason why I just explicitly work out for you to derive this simple relation that after this scale transformation, and this b is said to be that particular form, and we effectively get rid of this little t dependence in this rescaled Green's function. And this is sometimes a common trick in scaling analysis, because sometimes we need to fix, say, the field to be a zero field, or we fix our temperature to be exactly at the critical temperature. So let's just do the second setting. So we could imagine that we are exactly at the critical temperature. So we could choose little b to be the spatial vector r. So in that case, when t is exactly 0, here the Green's function depends only on distance. In that case, then this g at this position vector r and at 0 little t, which is at exactly this critical temperature, now takes this form with some power in r, and this non-trivial power exponent is given by minus 2 times d minus yh. So you could very easily see that, okay, from here. So now you could actually combine these two relations, because on the one hand, the first relation tells you that if you do the rescaling, and these two Green's functions differ by a power in t, little t, where effectively we somehow fix the field h. But the second relation tells you that the Green's function is a function of r exactly when the temperature is fixed at the critical temperature. So these two are common tricks that we can play and kind of manipulate this scaling form to whatever situation that we like to study. So in the first case, we like to study the situation where the field is somehow fixed, but this Green's function carry the temperature to some power. The second situation is when we study the temperature is actually fixed at critical temperature, but the Green's function is actually carry a spatial dependence on this power in R with some non-trivial exponent. Okay, so we can actually combine these two. When we combine these two conditions as a general situation where we at small but finite little t, and we could actually change our field so that this actually has to satisfy both conditions, right? So in general, we have that form, that this Green's function in a general case where we are not at exactly the transition temperature and we are not exactly at the zero field. So in that limit, this Green's function carry both the special degrees of freedom and also this little t degrees of freedom in a non-trivial power law fashion, where you can actually combine these two power law in the same power law as a function of r times little t to some power 1 over yt. So, but now you could compare this Green's function in the long distance limit that we derived already in many weeks ago, and compare this power law dependence in R between this Kadanoff's block spin language and the previously derived the correlation functions as a function of a power law in R, and you immediately see that this has to be satisfied, that d minus 2 plus eta has to be equal to 2 times d minus yh. So these two exponents should be identical, and as a result, we know that this yh is given by 1/2 of d plus 2 minus eta, and yt is given by 1 over nu that is known from the previous derivation, and its capital delta in Kadanoff's language is given by yh divided by yt. From the scaling relations, we know that this is also given by beta over nu, that this yh. In other words, we're almost there, except the value of the yh and yt, because eta is unknown and yh is also unknown. So we need to know what this yh is. So the way that we know this yh is not that we could derive right here, right now, because it requires RG transformations and solve for this RG scaling equations, and then we know this yh and also yt. So in other words, all the critical exponents are expressed in terms of the yh and yt that we know from there, and once we know the yh and yt, we know everything. So that's the power of Kadanoff's block spin kind of formalism, and I could just link everything that we know. So for example, from Wheaton's scaling hypothesis to the Kadanoff's block spin formalism, so they should be identical, and therefore the only thing that we need to know is the values of yt and yh. As I mentioned, the answer to that question requires the RG analysis, and so that will complete the circle that once we perform the RG transformation, which is based on the successive transformation of Kadanoff's block spin, kind of a scaling processes. And if we do this Kadanoff's processes many times, and then we could reach a fixed point for this coupling constant, and then we could solve this kind of iterative scaling equations for this effective coupling constants as a function of this rescaling factor. And then we could get this yt and yh by solving for the scaling equations. And the scaling equations, when we solve, they oftentimes lead to a power law dependence of this coupling constants as a function of this rescaling factor b. And that power law dependent is precisely the origin of this power law divergence near this transition point. And that is also a justification of why we should assume this non-trivial power law dependent of this little t and little h as we perform this rescaling. So now the only missing link here is to solve for this yt and yh. So that is the final task that we are going to do in the remaining 1 or 2 weeks of our class. So in the remaining time of our course, we will focus on the RG transformations and to derive the RG scaling equations based on Kadanoff's idea and to solve for the RG equation to get YT and YH. And after that, it looks that we're done. Okay, but there are other technical issues arising after this, but we will discuss that when we get there. Okay, so that's the complete story of Chapter 9 on this Kadanoff's block spin formalism. That is kind of the first step of the RG transformation, and we could actually justify the Witten's scaling hypothesis based on this scale transform Hamiltonian. So let's take a short break. When we come back, we will briefly introduce the RG, the concept of the RG, and the two steps in the RG transformation. Okay, so let's take a short break. Okay, so now let's formally introduce the renormalization group analysis. And first of all, so we should know how this RG transformation works, and later we will justify this RG transformation. Okay, so there are in general two steps in this RG analysis. The first step is to do the coarse graining procedure just like the Kadanoff did, and first we enlarge the lattice spacing to a factor b, where b is larger than 1, and then we rescale the lattice constant back to the original lattice so that this Rb is actually a factor of b smaller than the original distance, okay, because we rescale everything back to the original form. And we say that the effective Hamiltonian looks exactly the same form as the previous one before the coarse graining. And then we could do that many times, and then later we will define what this exact details of this coarse graining procedure involves. This involves the partial trace in the partition function, very similar to this Landau's coarse graining Landau free energy that we introduced earlier. So then we could relate this effective coupling constants before and after this coarse graining procedure, and then we could write down the equation for this kind of a revised or modified coupling constant in relation to the previous step, and that is so-called RG scaling equation. And we can solve the RG scaling equation as function of this scale factor b, and then we can know the power law singularities of this coupling constants if they have, and then we can identify this kind of a origin of the singular behavior by solving the RG scaling equation. As I mentioned, the system after this coarse graining procedure looks exactly the same as the original one, but with a modified coupling constant, and we will mathematically derive such a relation later. And a side remark, after we coarse grained this original Hamiltonian, and the Hamiltonian actually changes, right? So, and the new Hamiltonian is actually different from the original one because now we actually enlarge the lattice spacing, and therefore this new Hamiltonian describes the fluctuations that scale larger than the original lattice spacing, because now we are talking about the fluctuations of a new lattice spacing, which is b times a, and therefore we are further away from the critical point, as I mentioned. The correlation length actually gets reduced by a factor of b. So that's the characteristic of this RG steps. So we could right now just formulate this RG steps. First of all, let's just define our Hamiltonian in dimensionless way, that this is given by minus beta h, which is given by a coupling constant times the local interactions of spins, for example, the Ising spins, the theta, and refers to, say, for example, this nearest neighbor spin coupling of the Ising form Si dot Sj, something like that. But imagine that we not only have this nearest neighbor, we may have, say, Zeeman field term, or we may have the second neighbor interaction, and so on. Okay, so this is just a most general form of your Hamiltonian that can be divided into the summation over all this coupling constant times the interaction term, theta. Okay? So now, after we write down this starting Hamiltonian, we do the coarse-graining procedure. So the coarse-graining procedure is defined by a partial trace in the partition function over the block degrees of freedom. Remember that when we just divide the system into different blocks, and we could just perform a partial trace in the partition function to get rid of this microscopic degrees of freedom within each block, and then we could write down an effective Hamiltonian using these block spin variables. So as I mentioned, this Hamiltonian H prime after the coarse-graining procedure looks exactly the same as the previous one, except now this coupling constant changes from k to k prime, and again this spin degree of freedom is also changed to, say, Si prime in the block spin variable. So I guess that's enough for today, and next we will provide more details on how we actually perform this partial trace and what is the relation between k and k prime as we just iteratively perform such a coarse-graining procedure. You could imagine that I could just keep expanding this lattice constant to factor of b times a and b squared times a and b cubic times and so on and so forth. I could just coarse-grain the system once, twice, 3 times, as many times as possible, and this coupling constant now get changed to k prime, k double prime, k triple prime, whatever. So this procedure could go on forever. But things that we need to monitor is how this coupling constant flows as you perform each step of the coarse-graining procedure. And there's a relation between k and k prime precisely when we perform this partial trace. So that will be subject to the future studies, and in the remaining time of our lecture, so we will focus on this RG scaling equations and how to solve for the RG equation to get this fixed point, and also the critical exponents, especially yt and yh and so on. And therefore, once we solve this yt, yh, we know this scaling relations and we know the critical exponents. And we are, so to speak, we are almost finished, but not yet. Okay, so I guess that's enough stuff for you today. And please read the corresponding chapters, chapter 9, chapter 10, for details.